All right, so what we're going to do today is we're going to look at piecewise functions. We're also going to talk a little bit about circles and semicircles, although we really have already done that because yesterday, remember at the end of class, we looked at the equation of a circle. We started with the the real general form for the circle, which is the x minus h squared plus y minus a squared equals r squared. Then we reduced that down to if circles had a parent function, which they don't because they're not functions, but if they did, then it would be the unit circle. It's x squared plus y squared equals 1. And we just kind of generalized it a little bit to be x squared plus y squared equals r squared. And I think we graphed that semicircle. We just didn't, last night for homework, you were to fill in all of that, all the verbal stuff about semicircles. And before we really jump too much into the lesson, let's go ahead and finish that off. So take out your flip book. So let's see, our formula for semicircles was y equals the square root of r squared minus x squared. Okay, and that is a little bit of a kind of a general formula because it really r could be anything. That's just our radius, and we know that it came from that circle formula of x squared plus y squared equals r squared. We solved it for y. We got a plus or minus along the way. And the plus or minus would give us the entire circle, so we want it to be a function, and so therefore we took off the minus and just kept the positive square root, and that gave us that semicircle. And then graphically we know that this is centered at the origin with a radius of r units, so we'll go to the right r units, to the left r units, and then up r units, and here's what this graph looks like for us. So let's see what you came up with. Tell me about the domain. Brackets or parentheses? Brackets, good. So bracket, negative r to r bracket. Okay, so there's our domain. And that's obviously going to change depending on what the radius actually is. When I tell you y equals the square root of 16 minus x squared, now you know the radius is 4, and so my domain would go from negative 4 to positive 4. What about the range? What do you get?
0 to r.
Yep, 0 to r inclusive. Does that have any symmetry? Y-axis symmetry, which makes it an even function. Is it 1 to 1? No. Does it have any asymptotic behavior? No. Remember, an asymptote is a line that the graph approaches, and this line is not, this graph is not approaching any lines. Just because approaching would mean it kind of starts leveling off somewhere. That doesn't happen here. It just goes from one endpoint up to the other endpoint. Any x-intercepts? Yeah, positive and negative r. So our x-intercepts would be at plus or minus r0. Does it have a y-intercept? Y-intercept is 0, r. Does it have any minimum values? The minimum is the y-coordinate, which is 0, and that occurs at both r and negative r. Okay, so the actual minimum value is always the y-coordinate. So the minimum is 0. You might want to write it this way. The minimum is 0, which occurs at x equals plus or minus r. Okay. The actual minimum is the y-coordinate. And then what's the maximum? R, and where does it occur? At x equals 0. So maximum is a y-coordinate of r, which occurs at x equals 0.
And there's really not any in behavior here. An in behavior would indicate what happens as the graph goes towards infinity or negative infinity, and it's not doing that. It has definitive stopping places, definitive endpoints. So I don't see any reason for us to talk about that. Everybody good with that? So if I were to ask you to graph something like y equals the square root of 81 minus x squared plus 3, then how am I going to recognize that that's a semicircle? All right, 81 is a perfect square. It doesn't have to be, but I mean, I'm probably going to give you perfect squares just to make it easier for graphing. What else do you notice is unique to this? There's a square root, right? What's that? Okay, good. So, there's going to be a square root, but we're going to distinguish it from the square root function because your x is squared, right? If you go back and look at the square root function, it's the square root, but x to the first power. When you have the square root with x to the second power, then now that's probably going to be a semicircle, okay? And so you want to look at it in terms of that format of r squared minus x squared. So in this particular problem, what's the radius? Right, the radius is 9. What does that 3 do? It shifts it up 3, right? So we have a radius of 9, but then we're going to go 3 units up. So here's what this graph would look like without the shift. But then I'm going to take this entire graph and shift it 3 units up. So up 1, 2, 3. So there would be where this graph is now located. And we don't do anything extra, like we don't try and connect sometimes students want to connect right here. Why can't I do that? It's not part of the graph, and it wouldn't be a function, right? Because now you're telling me there's points along this line. There are no points along that line, okay? So now we don't want to do that. We just want to leave it as that semicircle, just that half of a circle, okay? I don't know if you recall, but when we did those worksheets early on in the semester, we did some problems where I asked you to find the area underneath the curve, like an area bounded by the curve in the x-axis. Kind of weird problems, remember that? In some cases, we were able to kind of separate that area out into different geometric shapes. Other cases, then we have to just like count the squares and like say, oh, there's half a square there, and that matches up with that half or something. Could you find the area under this? Good. I mean, do you know the formula for an area of a semicircle? Half the area of a circle, which is area of a circle, pi r squared, right? And so half of that then would be the area of a semicircle. Even with this problem, if you just envision this is a semicircle on top of a rectangle, right? And you can find the area of all of that that's underneath that that semicircle. Just finding area under graphs is going to be an important part of calculus. So being able to do that when you can do it like this, it's a good thing to recognize that you're able to find the area under a graph. Probably even an important part of statistics. Finding areas under normal curves. Yeah. No, it's amazing. Especially when the area under the normal curve is 1 unit. It represents 100% of the distribution, right? The whole normal curve comes from calculus. and finding area under curves. Amazing how this all comes together. Here it is. In 40 minutes, we've taught calculus, statistics, pre-calculus, and physics, all in one class period. Dang. All right, enough about semicircles. Put that away. You have some familiarity with piecewise functions. Okay, you didn't do a whole lot of it back in algebra trig. Did some, probably only in terms of lines, where you graphed one line up to a certain place and then stopped and started graphing a different line. We're going to kind of take that concept of a piecewise function and expand on it a little bit more. And we're going to take a little bit more in depth with piecewise functions. And they're actually really relevant. We've seen an example in here, I think early on in this unit where we did the problem with the car rental. Remember that? That it costs a certain amount for the first 7 days, then it costs a different amount from like day 8 till day 10. And then after that, it was, it'd be cheaper to just rent it for 2 weeks. So from day 10 to day 14, it was a different amount. So, piecewise functions do have relevance. In fact, our whole tax bracket for the United States is actually could be represented by a piecewise function, because people up to a certain amount, like you all, if you have jobs, when you file your taxes, you get everything back, right? So, that happens because you don't make enough to actually be someone responsible for paying taxes, right? So that up to a certain point, your tax bracket or what you would owe would be 0. But then at some point you start making money enough, at a certain point you make over the whatever it's poverty line or something, and then you are responsible for paying taxes. And there's a formula for determining how much you pay. It might be, sometimes you hear people refer to like a flat tax, which would be everybody just pays a certain percentage of what they make, period. And then, so that could be a way of representing it or so on. And then after you reach a certain point, you have to pay an increased amount of taxes because you make so much money. So it all, the amount that you have to pay changes based on your income. So it would really change based on the x coordinate. If you make less than $10,000, you pay this much in taxes, or you don't pay taxes at all. If you make between $10,000 and $50,000, you'll pay this much in taxes, or $50,000 to $150,000, you'll pay this much in taxes. If you make over $150,000, you pay this rate. And these different formulas are what are used to calculate the different amounts that you pay for each of those intervals. That's an example of a piecewise function. Okay? A piecewise function is going to say, for this domain, graph this function. Then, for this domain, graph a different function. And then, for this domain, graph a completely different function. And so on. Right? That's all a piecewise function is. And that's where the name really comes from, is that it really is a function made up of different pieces of graphs. So you might have a part of a line, and a part of a parabola, and part of a greatest integer function, all over different domains. All of them pieced together to create a function. Okay? Here's the most important thing that I want you to remember about this, because this will help when you start graphing them. These are called piecewise what? Functions. Right. That means your end product. What you're going to give me is your end product has to pass the vertical line test. If it doesn't, you did it wrong. Okay? So keep that in mind. In the end, all piecewise functions are functions. They've got to pass the vertical line test. Okay? All right, so let's just throw a little definition to all this. We've already kind of talked about it. Piecewise functions are functions. Function that graphs one function over one domain, another function over a different domain. You might have 3 or 4 or 5 or who knows how many functions. I mean, if we were to actually write the piecewise function that represents the tax bracket, then it would be this ungodly amount of functions all combined into one. Because it's just, everything changes depending on the amount of money that you make. But that's the idea of a piecewise function. It is a function that's comprised of different functions all graphed over their own domain. And what we do when we graph it is, you'll see, and we've seen an example of this already, we're going to have multiple functions. We might end up just graphing the entire function and then going back to that domain and saying, I'm only going to keep what's in the domain. So anything outside that domain, I'm going to erase that part of the graph and only keep the part that's within the given domain. All right, let's do some examples of this. Sorry, I'm going to have to make these up. Which is, let's see. Some examples. Hey. Will do. All right. All right, so let's make up a couple of piecewise functions here. We'll do y equals. Now, all piecewise functions are written in the same format. We have y equals, or, since they are functions, I might label it as f of x equals. It could be either one, doesn't matter. Just some kind of identification that the y values are outside of this bracket. Okay. So y equals or f of x equals. Then we put our function. So we'll just start off, maybe let's do an absolute value function. And then we give a domain. So I might say I want to graph this absolute value function for any x that's less than or equal to 3. And then I want to graph a, what should we graph? How about a cubic root function? For all x's that are greater than 3. Let me do this. Got a 4. That'll be a little bit better. All right, so all piecewise functions have the same format. We have the y equals. You got to have the y equals because it's got to be a function. So you've got to indicate your y coordinates, so y equals, and then you put a brace to combine all of your different functions, and then it's going to be function with its domain, function with its domain, and so on. And we can have more than 2. We might have 3 or 4 or 5 functions all listed there. You'll kind of pick up, or you probably figure out that you're definitely going to have a couple problems like this on your test on Friday, because I get more bang for my buck, right? Instead of me making you graph one function, now you've got to graph 2 different functions in the same problem. Okay? You got to know how to graph an absolute value function and a cubic root function. So you're going to get more out of one question.
Just to give all the information to this point on the test, I was just going to say, this is what it is, now graph it.
Graph that. Yep.
Make sure there's not any other way we're going to see this.
Which means? know how to do it, then you should be fine. All right, so here's our function. We're going to graph this. And it's just two different pieces, okay? You have the absolute value function, and then you have the cubic root function. Just take it one at a time. So let's graph the absolute value function. We know for an absolute value, the parent function is y equals the absolute value of x. And what are the points that are on that absolute value function? Okay. Now, based on how this function is written, what all are we going to do to that function? Go one to the right, 2 times y, and 3 up. And again, in that order, right? Remember, order matters. You've got to go in the correct order. So I'm going to move 1 to the right first, because I start inside the function, and then I work my way out, 2 times the y coordinates, and then 3 up. And again, if you want to write it all out first and then graph it, that's fine. You know, for example, here this says move everything 1 to the right. So all of my x coordinates are going to get 1 added to them. This says multiply the y coordinates by 2. And then shift 3 units up. So we'll add 3 to all the y coordinates. So my points are -1, 7. 0, 5, 1, 3, 2, 5, 3, 7, right? If all I was doing was graphing the absolute value function, there it is. Now it'd be done. Except that's not all I'm doing. Okay? This is a piecewise function, and I'm only going to graph this absolute value over this domain. Okay? So now I need to go back to my graph and say, I want to keep the part of the graph where x is less than or equal to 3. So it's right here where x is 3. So I'm going to imagine taking a pair of scissors and cutting the graph right there where x is 3. And I'm only keeping the part where x is less than 3. Which side will that be? Left or right? The left, right? Because that's where the x's are less than 3. So anything where x is greater than 3 gets erased. And I'm only keeping the part of the graph where the x's are less than 3. Less than or equal to, right? So at 3, is it going to be an open circle or a closed circle? Closed circle. So there's the absolute value function, but I've stopped at 3 because this piecewise function tells me only graph this piece up to where x is 3, and including 3. Okay, then I'm going to do the cubic root function. My parent function is y equals the cubic root of x. What are points that are on that parent function? -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. Okay. What am I doing to this parent function based on this equation? All right, good. Right 4, 5 times 3, 1 up. Okay. And if you want to write it out, do that. Write 4. Multiply the y coordinates by 3. Add 1. So our points will be at -4, -5. 3, -2. 4, 1. 5, 4. and then 12, 7. So here would be this cubic root function. But obviously, I can't have the entire cubic root function. It wouldn't be a, this piecewise function would not be a function. There's a domain, and the domain is that x has to be greater than 3. So I'm going to go to where 3 is on my graph, which is right there. If I want to keep the parts where x is greater than 3, which side will I keep? The right-hand side. Anything to the left of 3 gets erased. And at 3, am I using an open circle or a closed circle? An open circle this time, because it's just x is greater than 3. And there would be our piecewise function. So it graphs one function over one domain, and then a different function over its own domain. Now there's a term that's associated with functions that we haven't talked about yet, and it really comes into play when you start talking about piecewise functions, and that term is continuous. You may have heard that term before. But continuous, I mean, the name kind of gives it away. If something's continuous, well, what does that mean? Yeah, it just keeps on going, right? Would you think, based on context clues, that this graph is continuous or not?
Yes.
I'd say no. I got to pick up my pencil, right? I mean, to graph this, I had to go like this, but then I had to stop and pick up my pencil and come down here and then keep going. That is not continuous, okay? So this is not continuous. Continuous would mean that I would be able to graph the entire thing without ever having to pick up my pencil, without ever having to stop.
So what if there's two open circles?
Good question. What if there's two open circles? Like I'm graphing one function up to this point, there's an open circle there, and then the next function picks up from that.
No.
That is not continuous. Okay, it's a really good question. We use the open circle to indicate that there's not defined there, but graphically what's really happening is there's just like this little void, like this little blank space. Okay, so that really doesn't connect. Okay, that's a really good question. Now, if one of them's an open circle and one of them's a closed circle, then it is continuous. Okay, because they do end up connecting them. Okay, good question. What's the domain of this? Negative infinity to positive infinity, right? It is. It includes all values in the domain. Okay, because right here at 3, it is defined up here. So there is a defined value at 3. It's just the two pieces don't connect. So the domain is all real numbers. It's just not continuous at 3. Okay? All right, let's try another one together. What if that doesn't make much sense now, does it? Hold on. All right, let's try graphing this one. We have a quadratic function and then a square root function. Lord have mercy. That needs to be x is less than 2. And then the other one is x is greater than or equal to 2. All right, first graph is a quadratic, and it's in vertex form, which is nice because we know we like to graph from vertex form. So the parent function for quadratics is y equals x squared. And what are the points that are on a quadratic function? -2, 4, -1, 1, 0, 0, 1, and then 2, 4. Now looking at this function that's given, what are we doing to the original function? 4 to the right. 1/2 times y, and then 1 down. Okay? So we're going to add 4 to all the x coordinates. I'm going to multiply on the y coordinates by 1/2. And then I'm going to subtract 1. So those points are at 2, 1, 3, -1/2, 4, -1, 5, -1/2, and 6, 1. Is that right? So our parabola would look something like this. I don't want the entire parabola though. I'm only keeping the part where x is less than 2. So here is where x is 2. What part am I keeping? Left or right? The left, right? Because I want x is less than that. So that's going to be everything to the left. So anything to the right of 2 gets erased. And you might get to the point where you don't actually have to end up graphing the whole thing and erasing, but, you know, for now to start off with, and that's what I'm going to do. Is it going to be an open or a closed circle? An open. Okay. So it's just that little slice of the parabola. All right, next piece is a square root. And what's our parent function? All right, those are the points that are on the parent function for square roots. What all am I doing to those points? One half x, and then 3 down. Okay. Remember what's inside. When we multiply inside the function, we have to multiply by the reciprocal. So I'm multiplying all the x coordinates by 1/2, and then that -3 is on the outside. At the very end, that means to do a vertical shift of 3 units down. So I multiply all the x coordinates by 1/2. And then I'm subtract 3 from all the y coordinates. So go 3 units down. So we'll have 0, -3, 1/2, -2, 2, -1, and then 9/2, 0. So here's that square root function. But I don't want the entire function. I only want the part where x is greater than or equal to 2. So I'll go to where x is 2, which is right there. Which part am I keeping? Everything to the right, because I want to keep the part where x is greater than 2. Anything to the left gets erased. And is it going to be an open circle or a closed circle? It's closed. And is it continuous? No. Everybody good? All right, let me give you one to try. I got a +5. You try that one. Okay, so this one has a quadratic and a cubic, and you'll notice that the quadratic, I've given it to you in standard form. So you got a lot of work to do because you got to convert it from standard form to vertex form, then graph it, then deal with its domain, and then go to the cubic function, graph it, deal with its domain. So to start off with, we have the 2x squared plus 8x plus 5. Let's just convert that into vertex form. Okay, so from standard form to vertex form. So we'll start by finding the axis of symmetry, which ends up being what? -2. And then our vertex has an x-coordinate of -2. And we'll plug that in to find the y-coordinate. And what do you get when you find the y-coordinate? -3. Everybody find that? So our vertex is at -2, -3. So what is the vertex form of this function?
If you do, I did just a y-intercept and then here's the point, like over the symmetry, and it was like a whole different.
Yeah. What would be the vertex form? Good. Y equals 2 times x plus 2 squared minus 3. Remember, it's y equals a times x minus h squared plus k. And h and k come from our vertex. So that x minus h becomes x plus 2. The k becomes -3. And then the a value is the same a value from standard form. Okay? So this is the vertex form of that standard form. So I'm just going to copy it. I'm going to come back over here, paste it, and actually what I'm going to do is get rid of that standard form and then move this in its place. Maybe not. Okay, so there it goes. Okay, so I've just replaced the standard form with the vertex form. Our parent function we know is the quadratic, y equals x squared, which includes the points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. What all am I going to do to transform that parent function? 2 to the left, 2 times y, 3 down, in that order. So all the x coordinates, I'm going to subtract 2 from them. All the y coordinates, I'm going to multiply 2, and then subtract 3. So I'll have -4, 5. I'll have -3, -1. I'll have -2, -3. I'll have -1, -1. And I'll have 0, 5. So here would be the entire parabola. But we don't want the entire parabola. Where are we cutting this graph? At -3, which is right here. And which part am I keeping? Everything to the left, right? Because I want the x's that are less than that. So everything to the right of that goes away. And am I going to use an open circle or a closed circle? Closed circle. Right here, right? All right. Next function that's given to us is the cubic function. And what are the points that are on a cubic function? What all am I doing to this parent function? Okay, 5 to the left, 1/2 times y, and then 5 down, in that order, again. So we're subtracting 5 from all the x coordinates, so -2 minus 5 would be -7, -1 minus 5 would be -6, 0 minus 5 would be -5, -4, and -3. Then 1/2 times all the y coordinates, and then subtract 5. So we have -7, -9, so it's going to be down here. Then -6, -5.5. Then -5, -5. Then -4, -4.5. Then -3, -1. You'll notice that it's going through that point where the other one ended, right? And so here is this cubic function. We're cutting the graph at -3 again, which is that same point where we cut it before, except this time we're keeping everything to the right. Is it going to be an open circle or a closed circle? An open circle, but on top of the closed circle, so what's it going to look like? Closed circle. Okay, so there would be our graph. So what would be the domain of that function? All real numbers, right? This graph's pointing to the left, this one's pointing to the right. So it is going from -infinity to +infinity. What about the range? Yeah, -1 to +infinity. And we include -1. Is it 1 to 1? No, it doesn't pass the horizontal line test. Is it continuous? Yeah, it is continuous. I don't know if there's anything else to add. Sorry, well, I think that's good. All right, so I handed out your homework. It's that worksheet. If for some reason you lose that worksheet, the homework is online. So you can go to the website and you can access the worksheet there. You'll notice that 1, 2, 3, and 5, you're graphing, well actually 1 and 2, you're graphing parabolas from standard form. 3 and 5, you're graphing circles. And then 4, you're graphing a semicircle. And then 6, 7, 8, 9, and 10 are all piecewise functions.
Number 11 asks you of 6 through 10, which of those are continuous or not. And then 12 gives the problem to you in reverse. So instead of me giving you the function and you writing or graphing the function, now I'm giving you the graph and you have to write the function from the graph. Okay? What's that? So tomorrow we'll go over last night's homework, tonight's homework, and any questions you have from the study guide. And that'll all be part of your review for your test on Friday.
Oh, yeah, what was the quiz?
And the quiz, yeah, I'll give you the quiz after.
Oh.